All right, so the purpose of the video is to connect the ideas that we've discussed so far back to statistics, linear algebra, and start to, making the connection between the two, or between the three, I guess. Hopefully this doesn't last too long. Let me share my screen. All right, so the idea of the linear regression model. So y equals beta naught plus beta 1x. We've talked about that. We've talked about epsilon and being this normal random variable with an expected value 0 and a standard, I'm sorry, a variance of sigma squared. What that picture looks like. So we don't know the true values for beta 0, beta 1, and sigma squared. We're gonna use data to estimate these, and that's when that becomes the beta hat, the beta 1 hat, and we're gonna come up with an estimate for sigma squared hat today. But the picture would look something like this, where you have a data point, and then if you were to sample from that predictor multiple times, well, you'd have some sort of distribution around this value here, where epsilon is that expected value of 0, so we would expect it to be, on that line, but it will not necessarily, right? So it depends on, so this idea of spread around that line depends on what sigma squared is, what the true value of sigma squared is. So this is the sort of picture that I want you to think about whenever you're substituting a value into your model. Well, it's not going to always be exactly there, but sometimes it's going to be above, sometimes it's going to be below, but it really depends on what that variance is of epsilon, or the random process that we're talking about. Okay, so kind of come down here, so that y hat, we know the y hat is what lies on the line, so our expected response. Y itself is a random variable. Yeah, so what I'm saying is, like, take this picture and turn it on its side, and we expect this y1 hat. So this for this data point, for this predictor value that we put in, we expect a distribution of values depending on what this variance is. Okay, so that hopefully leads you to the question of, well, how do we actually estimate beta 0 and beta 1? So that's really the question. And so if you come down, so far what we've talked about is gradient descent. Gradient descent. Let me move that out of the way. But what we're gonna talk about just for a couple minutes is the linear algebra version, right? So the linear algebra least squares version. Least squares. And we want to connect the two. So I'm going to show you, hopefully in Python here in a few minutes, that these actually come out to be basically the same thing. Okay. So the idea here is the linear out. So what we're going to do is, there is no solution, right? So there is no solution to the problem xb equals y. And if you think about it, I mean, there is no, I mean, so for example here, so what we're talking about is, you remember xb, so you get these data points, these x values in here, and these data points are all on the line, and there is no m and b, there is no beta equals to beta 0 plus beta 1 x1. There is no way to get a solution to this, and that's why this vector y is above, is outside the column space, right? So the column space would be this column vector here, 1, 1, 1, 1, 1, and then x1, and all the data that goes along with the predictor, right? So this is this column here represents exactly what we've been talking about in class so far, those predictive variables. There is no line, there is no beta naught and beta 1 such that y equals beta naught plus beta 1 times x, right? So there's no m and b, there's no slope and intercept that's going to go through every single one of these points. And that's why this vector, this blue vector y, lies outside the column space of 1, 1, 1, 1, this column, and the x1, 1 through n. I think that thing says m in there, but it should actually say n, because there's n data points. Okay, and so the question is, well, how do we, so if that's true, if there is no solution xb such that I can get y, this idea here, there is no beta 0 and beta 1 such that I can multiply by x and get every single point that's in y here. If that's true, if you can't get that, then what's the best solution that we can get? Well, it's the one that lies right underneath, right? So this x beta is a vector, right? Because when you multiply x times beta, remember we get y hat, and y hat's a vector of values. And what we want is we want them to as close as possible to the y values. And that's what this sort of represents here. It's orthogonal, right? So it's a perpendicular to the column space. That's how we want it. So in other words, if I let xb be any other, if I choose beta 0 and beta 1 for any other values, maybe here, let me do it in another color. Maybe if they were, sort of lying over here, this vector, this e vector would be much longer than the one that's right underneath y. So that's the idea of minimizing this least squares, right? The magnitude of that vector. That's what I want to do. I want to make this e vector, this error vector, as small as possible. And the only way that we can do that is by lining it up right underneath the y. So that's really the only idea that you need to understand in order to be able to do the linear algebra solution to this. Actually, I take that back. You're going to have to understand that when you do the dot product between two vectors that are orthogonal to each other, that it equals 0. You might, if you don't remember that, you might want to go back and remember that one. But I think that's it. So let's just kind of go through the idea here, right? So let me start off in red. We know that x beta hat is going to be orthogonal to e, to my error vector. And the next question is, well, what is the error vector, right? So let me just write this in. I guess another thing you need to remember is that when you add, so this is a vector and that is a vector. So if I added those two red vectors together, then I would get the blue y vector, right? So that's just the tip to tail, if you remember that from calculus class. So let me just write this in this crazy color here. X b hat plus e, the error vector, so e is equal to the vector y, right? So that's what you would get if you just did the geometric addition of that vector plus that vector is going to be equal to the y. So now what we do is we just solve for e, and so we know e must be equal to, so this error vector must be equal to, let's see, I think it's y. So so take y, subtract xb, subtract x beta hat, not xb, but x beta hat. So this is what we're going to end up substituting into here, into this e vector. Okay. I'm gonna continue in this yellow color here for a second. And so if what did x beta hat is orthogonal, and now I'm going to substitute, instead of e, I'm going to put in this thing that we solved for. If it's orthogonal to y minus x beta hat, then what can we do? This is what I just talked about. So because they're orthogonal, that means I can do the dot product, or the dot product between the two would be equal to 0. Now, how do you do the dot product of two vectors? And again, go back to your linear algebra class. It's just the one vector. So if they're both column vectors, then what you do is you do the inner product, and remember what the inner product means. You put the transpose on the inner part of it. So it would just look like this. So x beta hat transpose, right? So that whole thing transpose times, matrix multiplication, right? So it would be y minus x beta hat. So I'm going to multiply these things together, and we better get the number 0. Why? Because they're orthogonal. Okay, so let's just do. So the next part is to remember that when you pull a transpose inside here, it becomes you switch the order of these two. Again, another linear algebra thing. If you don't remember that, again, go back and check that out. Let me put a smaller t here, and then so that part times y minus x beta hat still equal to 0. So now I'm going to just multiply these suckers out, and so I'm just going to get this piece times y. So you get beta hat transpose x transpose y times that y vector minus, again, take this part inside here, and we get beta hat transpose x transpose x, and then beta hat. I believe that's right. It looks right so far, I think. But we'll see it here at the end if everything works out. Okay, so I can multiply on the left-hand side by beta transpose inverse. And if I did that, beta inverse times 0 would be 0. Still the 0 vector. Oh, sorry. No, that's just the number 0. So if you did that, then you would basically get rid of this thing. And so you'd be left with x transpose y minus this thing would go away. And you just left with x transpose x beta hat equal to 0. And then just solve for what we're solving for. So I'm solving for beta hat, right? So we're going to get rid of that. So let's go. Let's see, x transpose y is equal to. Oh, I'm gonna put the thing that I'm solving for on the left hand side. So I'm gonna take it over, but I'm gonna flip the sides. So I'm gonna have x transpose x beta hat is equal to, bring that over, x transpose y, and then we're simply left with beta hat is equal to x transpose x inverse, and then what is that, x transpose y. Okay, so I claim that this will solve exactly the same. It will give us exactly the same as our gradient descent has done so far. Okay, you've probably seen this sucker before, but this is basically the linear algebra version of this. The problem with this is that it could possibly get too expensive. Calculating an inverse and doing these matrix multiplications is not, depending on how big your data is, this could be non-trivial as far as calculations goes. That's one reason. Well, that's one reason why we started using gradient descent. The other one is the fact that it's going to be used later on because where we don't have a linear algebra solution. So we wanted to see you, or we wanted you to have the ability to see this thing in this context that's relatively simple before you start using it, in a more difficult context. Okay, regardless of whether you use linear algebra or gradient descent, if you use the data, which is what we're doing here, this x is the data vector and y is the data. To estimate the parameters, that's when you start using the hat symbol. I mean, some people have an issue with that. So now your model is y equals to beta 0 hat because we use data plus beta 1 hat x1. So this becomes your model. When to use the hats and when don't you use the hats? Beta 0, if you used beta 0, you would say, hey, I know what beta 0 is. But in general, we don't really know what it is. So we use the data in order to estimate those things. All right, I think that's, oh, no, I'm sorry. I wanted to show you that this is true. So let's go to our, so what we did last class, I think this was the one that was in class. I'm going to shift enter through this whole thing. We're going to use gradient descent, shift enter. I'm going to use gradient descent. I'm going to ask you to do this tonight. You can stop the video right now and check this out yourself if you want to. But this is going to be one of your homework problems, is to find a function that does this. So shift enter, show the head. Okay, so what did I do with what does the standardized variable do? It did exactly the same thing we talked about in last class. It subtracts the mean, divides by the standard deviation of each one of our. So in other words, all I did was pass in horsepower, but I could have passed in more, and it would have gave me x2, x3, x4, and so on and so forth. But you kind of need to get something like this working. And then what we're going to do is we're going to solve for our thetas because we have standardized variables, and shift enter. This is nothing different than we did last class. You'll see that it comes out to I think the exact same numbers. And then I've created another function that you're going to need to create is one that converts it back from thetas back to our betas. And then shift enter and shift enter, right? So this is, I believe, exactly the same thing that we came up in class the other day for this horsepower MPG business. And you could plot that on a graph, just make sure it makes sense to you. But what I want to show now is the linear algebra sort of works out for us, and to show you how to do an inverse in NumPy. So let's let B. So do I even have a B? Yeah, B is not defined yet. So let's let B equal np dot linear algebra. So it's linear algebra dot, and you can do inv. I recommend doing what's called a pseudo inverse, just in case you have some some of your column vectors in your X matrix that are not necessarily independent. So what the pseudo inverse will do is it will always give you the inverse if all of them are independent, if all your columns are independent. If not, then it'll give you just an inverse with that will work for you, right? So you just use the pseudo inverse of this thing. And so X, let me make sure I get this right. So it's X transpose X. So X dot transpose, and remember matrix multiplication is that sign. So that's the inverse, and then matrix multiply, and then let me go back. X transpose Y. So X dot do that hopefully, and then we'll print P. Now the question is, what are we going to get here? Think about what X is right now. Am I going to get this number or am I going to get these two numbers, right? So right now, X is my X0 and X1, which represents my normalized or my standardized things, right? So I got my ones and I got my standardized X1. So I think when I hit Shift Enter here, I'm going to get this one, but that's not the one I want. But let's just find out what happens. Shift Enter. Yeah, so we get that guy. The question is, well, how do I get this one instead? Because that's really what we're going for. What would I have to do? I'd have to change my X's back to, instead of getting X1 here out. So let me just do that. Control C, Control V. Instead of X1, I want horsepower. Horsepower, hopefully. Then I'm going to do exactly the same. Control C. So I'm kind of lazy here. All right, so I did 39. So check out. I mean, it gets us. This one is more accurate right now because remember, this was an estimate based on gradient descent and when we decided to stop our. So I believe this would be the exact answer if I were gonna, if I were gonna do something with it. But again, what we wanted you to see was the gradient descent algorithm in action in something that we can already do, so that we can use it later because it's pretty important algorithm that we'll discuss. Okay, that's all I got. Hopefully you guys got something out of this one, and we will. I think I'm going to do it. I'm going to do another video of p-values and coefficient determination. I'm going to keep doing these because we don't necessarily get to all this in class. All right.